Welcome everyone to the first workshop for Advanced Track. And thank you to everyone who came. And I sent a form out in the chat. If you guys could fill that out, give like a few minutes, that would be appreciated, so we can kind of get a sense of what type of people we have attending the workshop. And on the slides, there's also a link to the slides, so you can follow along. If you need to go back and look at another slide, definitely would be good. So this is a quick overview of what Advanced Track is going to be. So we're going to be offering workshops from weeks 3 to 7. We're going to offer 5 workshops Wednesdays, so at this time every week. It'll be the same Zoom link, or we'll be in E6 conference room 372 if we go back in person. There's also a Discord forum. If you saw the announcement I made there, I'll also announce the workshops every week before they happen. And you can also discuss problems there that we work on during the workshop as well. The topic lineup for Advanced Track will be a bunch of relatively disparate topics. We'll have 3 workshops on graphs. So this week we'll be doing shortest paths. Workshop 3 will be doing MSTs and DSUs, and workshop 5 will be doing max flow. Also in workshop 2 and workshop 4, we'll be doing some other topics as well, strings and data structures, specifically seg trees. And possibly, if there's enough interest, we might host a 6th workshop on geometry, which is an important part about competitive programming, which is becoming more and more relevant in ICPC competitions. So the prerequisites for this track, since this is the advanced track, we're expecting a little bit more experience from attendees, so that we can kind of skip past all the fundamentals and go into more depth with all the algorithms, more advanced data structures. We expect prior coding experience, whether it's CS31, 32, and also some experience with algorithms and data structures is greatly recommended, since we'll be going into some intermediate to advanced level algorithms. And also previous competitive programming experience is also welcome, since we'll be working on websites that are doing competitive programming problems. So since we're talking about shortest paths this week, we're going to do a quick overview of graphs, just so that you remember. Graphs are defined as a set of vertices and edges. So that can represent either relationships between different locations on maps, or friendships between people, or like a social media web. However, in competitive programming, we normally talk about we just have numbers. We just have vertices, which are also called by nodes throughout the workshop. And they're just connected arbitrarily. And you can have cool results from them. So edges can either be unweighted or weighted, and directed or undirected. So these are pretty straightforward based on what they're called, but the unweighted graphs, unweighted edges are like this graph on the left here, where these are just showing that there's a connection between them. So let's say someone's like friends, like person A and person B are friends, and there would be like an edge between them. However, they can also be weighted in the sense that there's a certain cost from going from maybe one location to another location. It'll take a certain amount of time, or it'll be a certain amount of distance, which is variable. And edges can also be directed or undirected. So undirected means that you can go both ways along an edge, and directed could mean that it's a one-way street. You can only go one way or back, or is a different weight depending on the direction you go. So it might be longer to go one way, whereas if you come back, it's shorter. And paths in graphs are just sequences of vertices where all the vertices are connected and it creates a line. So it's what you would expect the path to be. And for this workshop, we'll be talking about shortest paths. So shortest paths will be the path with the least length. So for the case of a weighted graph, we'll be adding up all the weights of the edges in the path. For an unweighted, we might just consider which one has the least number of edges. Does anyone have any questions so far? All right, cool. And also when we're programming, when we're talking about graphs, we need some way to represent them because they seem pretty abstract, right? They're just a bunch of vertices floating in space. So the two main ways of representing graphs, which we'll discuss both of these actually in the algorithm that we talk about today, are adjacency lists and adjacency matrices. So adjacency lists are generally, if you are familiar with C++, there are like an array of vectors, or if you're in Java, it's like an array of array lists. So you would add on for each node all the edges that are coming out of it. So in this case, node 1 has 3 edges coming out of it, and you can put information about the edge, whether it's the weight of the edge or the destination of the edge, which is pretty mandatory. And then for adjacency matrix, we store it in a 2D matrix. So if you access the matrix at a, like, let's say one on row 1 and column 2, it means to the edge from row 1 to column 2, there is no edge because this is 0. And then it will be 1 if you have an edge there. And you can also store weighted graphs as well if you just put the weight instead of just a true or false, having an edge exist. So both of these are very powerful, but there are pros and cons to each of them that we will see as evident in the different algorithms that we talk about. So sometimes we want to use one, sometimes we want to use the other. So the first algorithm that we're going to talk about today is Dijkstra's algorithm. So this is, you may have heard of this algorithm. This is a very, very famous shortest path algorithm that you use all the time in competitive programming. So Dijkstra's algorithm works on weighted graphs, but the edges can't be, the edges have to be non-negative. And it also works on directed or undirected graphs. So, and you can translate all undirected graphs into directed graphs by just making 2 edges instead of 1. So the goal of Dijkstra algorithm is to find the shortest path from some source vertex or from some starting vertex, that's what the S kind of stands for, to all other vertices. So if you want to start at a certain location and you want to know how far away all other locations are, you would use Dijkstra's. So the way that it's done, a general like high overview of it, is that we create an array, a distance array that keeps track of the distance from your starting vertex to whatever vertex you want to get to. So D of V is going to it's going to store the working shortest path length that we're going to have. And I say working because what we're going to do is we're going to kind of iteratively find a shorter and shorter path until we end up at the shortest path. And I'll explain that process in a second. So for this algorithm, we initially set the distance to the source itself as 0, and then the distance to all other vertices as infinity. Because right now, all we know is that you can get, obviously, from the starting location, you can get to all other starting to itself with 0 cost or 0 distance. However, we don't know how to get to all the other vertices, so we're just going to set it to infinity. It's impossible right now. And we're also going to, for each node, we're going to keep track of an additional piece of information, whether or not that vertex is marked. And we're going to kind of see why we want to keep track of the marked or unmarked vertices. But initially, all the vertices are going to be unmarked, even the starting vertex. So once we have all that set up, we're going to follow this process. So we're going to go into a for loop n times, where n is the number of vertices. So for every vertex, we're going to have to run this kind of in inner loop. And what we're going to do is we're going to choose the unmarked vertex V, so any of the unmarked vertices, with the minimum working distance, and we're going to mark it. And then we're going to perform relaxations from all the edges coming from that V, that vertex V that we chose. So what are relaxations? So relaxations are kind of like that like optimization I was talking about before, where we find a long path and we kind of cut it down and make it shorter and shorter. So that's what we're kind of doing with these relaxations. So what a relaxation in this case is, what it is that if we have an edge, let's say from U to V or from V to U, we want to kind of do this test right here with this if statement. So if you can get from the starting vertex to a vertex V, and then travel along that edge from V to U, if that total distance is shorter than the working distance we have now, we have found a shorter way of getting there, because we know, because D of V kind of stores the current path we have now from the starting vertex to vertex V. So if we just add in that one edge, we can kind of see, oh, this is a new path. This is a faster path, so we can choose this instead, or a shorter path. And this second line would just be setting that value to what we have found. So so the intuition for Dijkstra's is that you're going to kind of iteratively decrease the distance to all the nodes until we end up at the optimal one. Just one note is that this slide deck also includes proofs, but they have been hidden because didn't want to like overwhelm everyone with explicit proofs of all of these algorithms. But if you're interested, you can definitely open up the slides on your own and look at them. I think they're definitely interesting, and check them out if you're interested. Okay, so I'm going to run through an example of it working out, because just talking about it isn't too clear. So this is kind of like a sample graph that we have here. So this is our sample graph. And right here. And we have the initialization of the two arrays that we talked about before. So we're going to have a distance array. So I drew this like this in as like kind of a 2D array, but it's actually just two 1D arrays, because one's going to be storing integers, the other one's going to be storing kind of booleans, or having it marked or unmarked. So we're going to initialize it, right? We have it initialized first. The distance to the first one is 0, and the distance to all the other ones is infinity. And these are all unmarked. So I'm going to leave them blank for now. And as I mark them, I'm going to kind of fill them in. So our source in this case is going to be, we're going to start from 0. And we're going to look at all of them. We're going to perform relaxations from it. So obviously this one's the shortest path, because 0 is smaller than all the other infinities. So we're going to mark it. And then we're going to look at all the edges coming out of 0. So that's going to be this edge. It's going to be this edge, and it's going to be this edge. Okay, so we're going to look at them one at a time. So first we want to see, okay, we have this edge from 0 to 1, and it has a cost of 3. So we do our relaxation, right? We're going to calculate the current distance. So the current distance to 1 is infinity, which is going to be greater than basically anything we have. And that's going to be the distance to 0 plus the weight, which is going to be 3, which in this case is going to be 0 plus 3, so it's going to be 3. Obviously 3 is less than infinity, so we're going to do the operation. We're going to set the distance, we're going to update it, the distance to 1 as 3. And we're going to repeat this for the other two, since we know obviously the distance to all the other ones are also going to be infinity. We know the distance to 3 and the distance to 4 are going to be set to 7 and 8 respectively. So now we can really just treat these edges, since we've already considered them. We can kind of just mark them, because we won't ever end up considering them again. Okay, so now we repeat the process. So we're going to look for the shortest, the unmarked vertex with the shortest working distance, and that's going to be vertex 1. So we're going to mark it, and we're going to look at all the vertices that are coming out of vertex 1. So we're going to have this one, and this one. So we're going to do the same thing again, and we're going to consider the distances. So if we go from 0 to 1 back to 0, obviously we're going to have, the distance to 0 right now is equal to 0. And this is not greater than the distance to 1 plus 2, which is actually equal to 5. So since 0 is not greater than 5, we're not going to do this relaxation, because we found a worse path to follow. For those of you that are just joining us, please fill out the form. I sent it in the chat. I'll send it out again so we can get a demographic of who's attending. So that one doesn't work. We're going to try the other one. So from 1 to 3, that works. 3, distance to 3 is 7, right? And 7 is less than 6, where we're going to have 3 plus 3, because the distance to 3 right now is 7, which is greater than the distance to 1 plus the edge length, which is 3, which is equal to 6. So we're going to set this equal 6. Continue. And for this last one, 2 is infinity. So obviously we can switch this out with the distance. So it's going to be 3 plus 1. So it's going to be 4. Okay. And then now we're going to repeat this process again. I'm going to go kind of faster now since we kind of got a sense of what's happening. So we're going to mark 4. We're going to look at the edges that we're going to consider. There are actually no edges that we can consider because there's no edges coming out of 2. So we can continue forward. Edge node 3 is the next smallest one with a distance, working distance of 6. We can see that there is one more edge coming out of 3. And that actually gives us a shorter distance because there's actually this one as well. So let's actually do this one first. So the distance to 2 is equal to 4, which is not greater than the distance to 3 plus 2. Distance is 3 is 6. So 6 plus 2 is 8. And that's not true. However, the distance to 4 is equal to 8, which is greater than the distance of 3 plus 1, which is equal to 7. So now we can update this last one to 7, and now we are done. So we have found the shortest paths to all of the other nodes starting from vertex 0. They don't have any questions, anything confusing. All right, great. So now that we've marked all the vertices, we're done. There's no more vertices to consider, and we've found the shortest path for all of them. And you can notice that once we mark a vertex, we never come back to it. We never kind of alter it. We don't need to consider it. All right. So what is the complexity of this algorithm? Because in competitive programming, we want to know if our programs can run in time with the problem constraints that we have. So for this naive implementation, right, the complexity is going to be v squared plus e. And that's because there's a for loop for all the vertices. So it's going to be each v iteration checks on average half of the other vertices, because the number of vertices you check kind of decrease every time you go through that for loop, which is where the v squared comes from. And then the relaxations are constant time, but you need to do it for each edge. Notice that in the example we did, we never went back to an edge once we considered it. So each edge is going to be considered once with constant time. So we're going to add in an e there. Okay. However, we kind of want something faster than quadratic because that's not sometimes won't fit into the constraints that we have. So the speed up that we're going to look for is to speed up the time that it takes to find the unmarked D, because that's taking a lot of time, right? We're spending linear time searching throughout the vertices. There must be some data structure that we can use to kind of speed this up. And we can actually speed this up using a priority queue. So what a priority queue is it allows you to insert kind of like numbers or objects into the queue, and it automatically sorts all the values and gives you like the largest one. Or in this case, we're looking for the smallest one. So it'll keep track of which one's the smallest number in that queue, and you can grab it from the top in constant time. So it takes a logarithmic time to insert it, and it takes a constant time to take out the smallest element, which is what we're looking for. So now this allows us to create a new complexity of O of v plus e log e, because each edge is gonna, each relaxation is gonna insert an edge into that priority queue. And but each of the v iterations are going to take constant time, because we're just going to be able to grab the shortest working distance that we have in constant time. And we can actually get it down to a faster time, but that's not really necessary most of the time. Pretty much all the time. I haven't personally implemented this, and it uses Fibonacci heaps. There's a really funny article my friend sent me a long time ago about Fibonacci heaps and how it ruins someone's life. So if you're interested in reading that article, I have it linked there. But yeah, so most of the time, this new complexity works with priority queues. So what I want you to do is kind of try and implement this, because I think this is an important skill that all competitive programmers should have, is implementing these pretty standard algorithms. So you should be able to kind of come up with them, or at least understand kind of the structure of them. So here's some pseudocode for what Dijkstra's what we just talked about. The walrus operator here is to set a variable. So what you would in C++ or Java, you would just use the equal sign to set. And yeah, and I can walk through this one more time. So we're going to have all the initialization right here for the vertices, for the distances. And one thing you want to notice in the pseudocode is that it actually keeps track of the paths itself. So you notice that when we did the example, we only kept track of the distance of the path. So what is the shortest distance to it? But we have no way of recovering the path itself. By adding in one more array, we are able to keep track of kind of like the previous node that we came from, the previous vertex that we came from, and kind of backtrack along from the final destination of our path. So every time we do the relaxation, we're going to also keep track of where the path came from. And then, so where we want to insert the priority queue is right here. So we want to define the priority queue before we enter the main loop. And instead of searching for the node with the smallest distance, we're going to read from the priority queue instead. And then in this relaxation part, we're going to insert it into the priority queue every time something is relaxed. And you might be wondering, like, oh, we might insert some vertices multiple times into the priority queue. In this case, it won't matter because the priority queue, because we're always going to be taking the smallest distance to some node. So since if we have some longer path to it, we'll consider the shorter path first using the priority queue before we consider the longer path. So we actually don't need to worry about it too much. So when we're reading from the priority queue, we just need to make sure we haven't, the vertex that it tells us has the shortest path isn't already marked. And yeah, so I want to give you guys some time to kind of maybe implement it. CSCS is a catalog of pretty canonical standard competitive programming problems. And so it gives like a good benchmark for checking if your algorithm works or not. It's pretty quick and easy to make an account. But yeah, I want everyone to kind of maybe try for, I'll give you guys maybe 10, 15 minutes to try and implement it yourself in the language of your choice. And there are a bunch of officers here as well. And we can definitely help out with any debugging or anything. So stop the recording for a second. And I'll give you guys some time to work on it. All right, so now we're going to talk about the next algorithm that we have. So Bellman-Ford algorithm. So the Bellman-Ford algorithm is kind of fixes one hole in the Dijkstra's algorithm, which is there can't be negative edges. And that's because we kind of greedily choose the edges because we know that a path can't ever get better once it's considered. But sometimes the negative edges might complicate that. So the Bellman-Ford algorithm works for all edge weights, all integer edge weights, probably rational edge weights as well. And what it can do is it can also detect negative cycles in graphs. So what are negative cycles? So negative cycles are cycles in graphs, so where you can go from a path from a vertex to itself. And by going around this cycle, you're going to result in a negative distance or a negative cost, which doesn't really help our cause because we're looking for the shortest path. So if some path includes any part of the cycle, we could just keep going around that negative cycle and then keep on getting a shorter and shorter path. So that kind of doesn't help. So if we're doing any problem that's kind of have like a negative cycle hidden inside, all the shortest paths that we calculate don't really mean anything. So we need to kind of say, oh, okay, this is a bad setup, you know? So this works on weighted, directed, or undirected graphs. And what it does is it does the same thing. So it's a single source shortest path. So you pick a source vertex and you want to find the shortest path to all of the vertices. So the way that it works, so we're not going to have a marked or unmarked Boolean array to keep track of vertices. We're just going to have that distance, that working distance array. We're going to set it up the same way as we did with Dijkstra's. So the distance to the starting node is 0. Initially, and the distance to everything else is infinity. We don't know how to get there yet. Then we repeat this n-1 times, this process inside. And what we're going to do is we're going to take every edge and do a relaxation with it. So it's going to be the same relaxation as in Dijkstra's. So we're going to consider the path to the initial part of the edge. So the edge UV, we're going to go from S to U, and then take the edge UV to the final destination of V. And if that is shorter than, well, this is backwards, apologies. This should be, these U and V should be switched. But the idea is there. So we're going to look at two different paths, working paths that we have. If one is better, we're going to pick that one, the one with the new edge that we're considering. So, and then finally, once we're done with that, we'll have all the shortest paths. And to check for negative cycles, we're going to repeat it one more time. Repeat it one more time. And if any more relaxations occur, then we know that a negative edge cycle exists, or a negative cycle exists. And so the intuition for this algorithm, because you think it's a lot different from Dijkstra's. We're trying to look for like kind of the best that we have right now and kind of remove it from the search pool. In this case, we're just trying everything repeatedly. So how can that possibly work in finding the shortest path? So the intuition you should have for this problem, and this was also explained in the proof that is also in the slide deck, is that every time we run this relaxation process, it finds all shortest paths with k edges, where k is the iteration that we're on. So we're going to go up to n-1 iterations with this outside array, with this outside loop. So when we do the first loop, when we do the first pass, we're going to find all of the shortest paths from the source node that are one edge long. And then we're going to repeat that over and over again. And we're going to find all of the shortest paths that are up to n-1 edges, that contain n-1 edges in the path. And using that intuition, you get another piece of intuition, which is that shortest paths have to be less than n edges long. And this is like kind of like the pigeonhole principle, if you guys have heard of that before, where if you have a shortest path with n or more edges, that means it contains n+1 or more vertices, unique, n+1 vertices. And since for a path to not contain a cycle, it can have only up to n vertices, because there are only n vertices and unique vertices in the graph. So if there's any more than that, any more contained in the path, there has to be some repetition, which also implies there's some cycle. And if there's no negative cycles, then it has to be a positive cycle, and we can kind of get rid of that cycle and make it shorter, make that path shorter. I hope that intuition kind of makes sense. So we're kind of building up shortest paths with increasing lengths in terms of the number of edges, not the total path length, but the number of edges. So this last part is just seeing, can we make something shorter by adding more edges? That's the same thing. That's equivalent to looking for a negative cycle. Okay. So we're going to walk through the same. We're going to do a similar example. So for Bellman-Ford, we're going to have a similar, it's going to be a little bit more reduced because we need to consider every edge individually. And we have the same setup. So what we're going to do, I'm going to, for the sake of making this look interesting, I'm going to walk through the edges backwards. So I'm going to go from right to left. So we're going to consider this edge. So if it's infinity, we kind of have to skip the relaxation because it doesn't make sense to add a constant value to an infinity. So in this case, 3 and 2 are both infinity, right? So we skip it. Okay. And we go, we try this one and this. These two edges also have infinities on both ends in terms of our working distance to the two sides of the edges. However, these three edges are cool. They are working just fine. So we can add them in. When we do the relaxation, it's just 0 plus 3, 0 plus 7, 0 plus 8. So that's 1, 3, and 4. So we're going to put that in. So 3, 7, 8. Great. So we did one iteration. So we're going to do up to 3 iterations. So we're going to do 4 iterations actually, because we have 5 nodes. Please note that these are 0 indexed. Most of the time in problems, you're going to have to 0 index all of your vertices it just makes things easier. Instead of having like an array of n plus 1 size, you can just make it size of n, stuff like that. So we're going to do this again. We're going to consider rightmost one. So we have 2. So we can get to 3 now. So that means we can consider the relaxation, right? So we have distance to 2 is equal to infinity, but that's going to be greater than distance to 3 plus distance of 2, right? From this edge width. So we're going to do the modification. We're going to put this in. We'll put this as 9. Okay. But you can kind of see here, we have a path. We have a path here that's better. So we're going to get to it, right? Because this is just the second iteration, which means we're going to find all paths of 2 edges, right? So we're going to get to that in a bit. And then we're going to consider this edge. So this edge is shorter, right? Because this is 6 versus 7. So the distance to 3 is equal to 7 right now, which is greater than the distance to 1 plus 3, which is 6. So we're going to replace this with 6. Great. And then finally, we consider all the other ones again, but they're all the same. Notably, this one's also the same because 7 plus 1 is 8, which is the same distance here. So note that this is not a greater than or equal to sign. This is just a greater than sign. So strictly greater. Okay, and then we do it one more time. So this is our third iteration. And if we, all these other vertices aren't going to change. This one, this one, this one, this one, this one kind of have reached their end point. But this last edge right here is going to have an effect because we're going to consider distance to 3 is 6. And that's greater than, or sorry, my bad. Distance to 2 is equal to 9, which is greater than the distance to 3 plus the edge 2. Right now, this distance to 3 is actually lowered from 7 to 6. So it's going to be equal to 8. And that is strictly smaller. So we can update this to also be 8. And if we run this one more time, if you go through the math, you can see that no relaxations occur. That's actually a minor speed up that you can have in Bellman-Ford, where you exit out of the graph once no more relaxations occur. Because obviously for the next iterations after that, there's no relaxation going to occur anyways. So that's kind of a minor speed up, but it's not a big speed up. And now we're done. And then once we run this one more time, that nth time, right, in this case, the 5th iteration, there's going to be no more relaxations, which means there's no negative edge cycle. Okay. But what if there was a negative edge cycle? So you can see here, obviously, if you go from here to here to here, you're going to have -2 length. So we just added in this negative edge. And we're going to kind of see what happens to the algorithm when we do that. So we're going to do the same process as before. We're going to consider this edge. Both are infinity. We don't care. This edge, also, we don't mind because this distance right here is still infinity. And this edge and this edge are also both infinities. So we don't, they have endpoints at infinity. This working distance is infinity. So we're just going to update these 3 for the first iteration. So we're just going to kind of add it there. So we have 3 to 1. 7 and 8. 3, 7, and 8. Okay, and then we're going to do it one more time. So now we can consider this guy, and we can get a distance of 9 to 2. Right, it's kind of the same thing as before. And then we can consider this guy as well for node 3. The working distance goes from 7 to 6. And then finally, we consider this back edge, this negative edge right here. So we go from 3 to 0. So the distance from 0 is equal to 0. But this is actually greater than the distance from 3, right? Right now it is 6 plus -8, which is equal to -2. And we can update this to be -2. And things start getting kind of out of control because we have a negative edge situation. So now if we do this for the 3rd time, we're going to have that reduction that we did before. And we're also going to have, we're going to consider this edge once more. And we're also going to update this edge. So the distance to 1 is going to go from 3 to 1 instead. And this distance from, we're going to consider this edge from 3 to 0 again. And that's going to reduce as well. to actually, sorry, that's not going to reduce. So what you're going to see is that this edge, so we considered this edge last time, and this resulted in a reduction. And then the next cycle, we have a reduction in distance on this edge. And you can kind of see, we can kind of guess that it's going to continue around in like a loop. It's going to keep reducing one by one. This we're going to keep repeating over and over again. And you can kind of work this through yourself as well. And you can see that eventually it's just going to keep repeating. So when we do the fifth iteration, right, the outside iteration, we're checking for more extra relaxations. A relaxation is going to occur, and then we're going to find a negative edge. We have detected a negative cycle. Sorry. No implementation for this one, but we can talk about the complexity. So for our case, the complexity is going to be VE because we do n-1 iterations, which is basically V with the constant added on. And for each one of the iterations, we do E relaxations. We touch all of the edges and we consider them. So the consequences of this is basically just a slower but more powerful version of Dijkstra. So we normally don't use it in shortest path problems, but it's useful for problems that are just specifically targeted towards negative edge cycles. So if you went to training last week, there was a problem about detecting negative cycles, which was useful. And you can also do this edge negative cycle detection with the next algorithm we're talking about too. And here's some pseudocode if you want to look through it. And yeah, but we won't be implementing this today. Finally, our last algorithm is going to be Floyd-Warshall. So Floyd-Warshall is going to tackle that last problem. So both algorithms gave us the shortest distance from one source vertex. For Floyd-Warshall, we're going to find the shortest distances or the shortest paths between all pairs of vertices in the graph. So this works on weighted, directed, or undirected. This also works with negative edges, but it's a little more involved. And yeah, and the intuition that I want you to have when I go into the explanation of the algorithm, because it's actually very simple. It's spoiler, it's just 3 loops. The intuition is that you're going to be adding intermediate vertices to adding each intermediate vertex to all shortest paths. So it's like you have 2 shortest paths and you're connecting them together with a vertex, and you're connecting them together, and you keep repeatedly adding, like inserting vertices into the shortest paths and kind of linking them together. And this is it. This is the whole pseudocode. So actually, minus this like first 6 lines, this is the bulk of the code. These 5 lines. So the first 6 lines are just initialization. So instead of having a distance 1D array, we're going to have a 2D array. And what it's going to do is going to keep track of the shortest distance from U to V. So now instead of just accessing the distance array with one vertex, your destination vertex, you need the starting location and the ending location. So the way that we initialize it is that we set all distances for vertices to itself to 0, because obviously you can always go to yourself. And we set all the edges that we know in the graph to their edge weights. And then for everything else, we set it to infinity because we don't know how to get there yet. And then for the bulk of the thing, it's just going to be these 3 for loops. So we're going to have K, and that's going to be the intermediate vertex that you kind of want to think about. And then we're going to try all possible paths with this IJ thing. And this is very similar to the relaxation that we saw before, but in this case, it's slightly different, where we're kind of, you can see we're linking together paths from I to K, then from that go from I to K and K to J, and we're comparing it to a path that we have directly from I to J. And it's kind of like we're trying everything. And it goes, I go more into the intuition and write out the actual proof in the slide deck. So you can check that out too. And it just returns a distance. You can augment this to also save the path itself. And by doing that, you're going to put it in this if statement, and it's going to store kind of like the path from, it's going to store intermediate paths, and you're going to kind of build outwards. But this is basically it. It's just 3 for loops. I don't know if we have enough time to run through examples, but but I will post the PDF of the examples I have set up, so you can kind of work through it yourself as well. Yeah, so we're going to skip this for now for time's sake. So the Floyd-Warshall algorithm, we have the complexity. So we always want to consider this. So the complexity for this is V cubed, because obviously it's 3 for loops. Each loop goes for every vertex. It's pretty straightforward. This means that for problems with 500 or less vertices, we can use. If there are more than 500, it gets kind of close to the upper bound of how much time we have, how many calculations we have. So generally, if you see graph problems with 500, you can kind of guess that, oh, this might work with Floyd-Warshall, or it might be something even more complicated. I don't know. And if something's bigger than that, maybe 10 to the 5, something much larger, Dijkstra is probably the move. Or if you have like maybe 1,000 or like 2,000, you might be able to get away with Bellman-Ford. And then, yeah, and I talked about from before, you can recover the shortest path as well by doing an augmentation. And then you can also use this to find negative cycles. And the reason why you would use this is because Bellman-Ford only finds negative cycles that you can reach from the starting vertex that you choose. In this case, Floyd-Warshall finds shortest paths from all pairs. So it's able to find negative cycles in the entire graph as a whole. But we won't be talking about that. Definitely search it up if you're interested. And I will give you a little bit of time for doing that implementation. It should be pretty quick if you guys want to try. It's just 3 for loops, and just make sure you have the initialization correct, and you check the edge case where you're adding infinities. So when you're doing this check right here, this if statement, you might want to add in something about, oh, if the distance from I to K and from K to J, if either of them are infinity, maybe skip it right for now, and you can kind of come back to it. So I'll give you guys maybe a few minutes. Should be pretty quick to write this up. Make sure you have like overflow and stuff, overflow protection, because I think this problem has pretty big numbers, so you might need to do that. Yeah, so I'll give you guys a little bit of time for that. All right, so now we're going to go over some practice problems, some example problems that I think are pretty applicable to the algorithms that we talked about today. Please read through the problem statement and kind of think about it for a second. Since we're running a little behind schedule, there are a few links. I'll drop a link to the problem in chat, and I'll just put some hints up as well for you to think about. I hope you guys were able to read through the problem. So the basic idea is that we have a bunch of junctions. Some junctions you can grab stones from, an infinite pile of stones, but they're stones of different varieties. So there are a bunch of different types of stones, and you are an alchemist, so you can combine certain specific quantities and specific types of stones together to form different stones. And you can use those crafting recipes to combine it together. And your goal is to create a golden stone, which you can't get directly from any of the junctions. You have to craft from the junctions. And however, these stones, you can only carry them one at a time, and you can move them in between junctions as well. So you can bring a stone from a different junction to another one, which uses up 1 unit of your energy. So how can we convert this problem into a shortest path problem? Because this is kind of like it's hidden inside. When I did this in competition, I definitely thought it was like a dynamic programming problem. But this is a shortest path problem actually, which is interesting. So what we should do is look at hint 2, and we need to consider what we want to think of as a vertex. So we can define each vertex by a junction and a stone. And the distance, which is going to be the cost in this case of the energy used, is going to be the amount of energy used to bring a stone S, a specific type of stone, to a specific junction. And that's because you can only do the recipes when all the stones are together at one junction. And once you have that information, you can construct edges between them. So obviously, when you're going from one junction to the other, it's going to cost you one energy, or a distance of one between junctions that are adjacent and have the same stone type. So this is kind of the same idea as moving one stone from one junction to the other. And then another type of edge you can have is kind of traversing that second dimension you have, the dimension of the stone type. And that's going to be, you're going to be using the recipes instead. So the moving the junctions is going to be kind of like edges across the first dimension, and then edges across the other dimension are going to be the recipes. And the cost in that case, or the distance of that edge, is going to be a little bit more different because it's defined by the cost of a bunch of different stones, because you're kind of gathering them together, right? So if you have a recipe with two stones of type 1 and one stone of type 2, the cost of applying a recipe is just going to be the cost of getting two stones of type 1 and one stone of type 2 at the junction you're currently at. And if you do the math and count out how many possible vertices there can be and how many possible edges you need to actually consider, it ends up being within the time constraints of Dijkstra's. So we can actually just use Dijkstra's straight up once we have these edges set. You do have to modify Dijkstra's a little bit so that it considers recipes, because recipes aren't exactly a fixed edge weight. It's more of like a something you need to just consider individually. So for the first test set, the test cases are small enough that you can use Bellman-Ford actually, which we talked about as well. Or you could just use good old Dijkstra's since there are no negative edges. And then the answer then is going to be, once you run Dijkstra's, you go through all the edges, the answer is going to be the minimum of getting the golden stone over all the junctions, because maybe it's easier to make a golden stone at one junction than at another junction, because maybe the stones are kind of centralized around some area or something like that.
Oh, Robert, could you go over the second type of edge again?
Yeah, so when you apply a recipe, what you're doing is basically you're gathering all of the stone types into one junction, and then you're doing that recipe. And then the problem setup, that recipe is like free. It doesn't use any energy. It's just the energy of procuring all of those stones. So the energy to procure all those stones is going to be D of JS, where you're at some junction J and you want some stone S. If you want multiple of those stones, you can just multiply by how many you want. And to get the total cost of getting all your items, to all your ingredients to create that stone is just the sum over all different types of the stones you need. So then your distance to, let's say you're creating the golden stone. So your distance from your D of J1 is just going to be equal to the sum of all of the ingredients that you need. And then you can kind of think of it like, oh, once you get that ingredient, you can kind of distribute it across all the other junctions. Maybe it's cheaper to construct the golden, or maybe some intermediate stone somewhere, or like there's two different central locations where you can construct or create a intermediate stone, kind of like spreads out. Yeah. So yeah, I didn't mention this, but your initialization is going to be kind of similar. So to create your initialization is going to be based off of which junctions are selling which stones. So if a junction's, you can procure like a specific type of stone at a specific junction, you can set that cost to 0 because it's infinite. There's infinitely many stones you can grab from there. Else you set it to infinity. So very similar to the normal Dijkstra setup.
Yeah, so I guess the thing that I'm still all confused on is it seems like you're needing to label or to give edges in this graph weights, which are calculated based on this graph. Mm-hmm. Do you need to like do it in a certain order? Like,
yeah, I think my implementation, you ended up needing to do all of like the movement edges where you're like moving all the stones, and then you apply all the recipes, because I think there's not that many recipes. I don't know what the exact limit is, but there aren't that many recipes to consider, I think. Okay. So moving on.
Sorry,
So
yeah. I'm still stuck. Like, let's say you're saying like if we do all the movement edges first and in one pass, and then all of the recipe edges in another pass, doesn't that assume that like movement is always like better than recipe if you can do it? But like that might not be true, right? Like what if you have a recipe that converts like one stone of type A to one stone of type B, and like a type A producing vertex is way closer than a type B producing vertex? Then in order to evaluate the cost of like a recipe that uses like type B stones at this vertex, you need to know about the recipe for producing them from type A stones from the neighboring vertex. Because if you think that you have to get the type B stones from like the other side of the map, then you're going to be wrong. Maybe I'm missing something.
yeah, I'm looking at my implementation right now. It looks like for my relaxations, I do all the recipes first, and then I propagate the minimum cost. So it might be. Let's see. Yeah, it I guess seems like it works. Okay, yeah, so in my implementation, so you pop out a single vertex, so it's going to be the city plus the stone, and then every time that happens, you redo all of the recipes. And if any of the recipes, the cost of any of the rest, like if you haven't considered grabbing a stone and bringing it to your current location that you're working on, you just skip that recipe. And then after you do that, you propagate every stone. It looks like you try every stone you try every stone type, and then you propagate along all the edges, like the actual like walking edges, where you bring all of the stones you can make to an outer city or a junction that's connected to. So it looks like that ends up being the right order to do stuff in. Because I think there aren't that many recipes. So I think you can do all of the recipes every time. Let me see how many recipes there are.
Okay,
300 recipes.
I'll think about it more.
Yeah. Yeah. Yeah, because that kind of skips your case where it's like, oh, you haven't considered getting all of the stones for all of the recipes yet. You don't know which recipe to consider, but it looks like it seems like you can just do all of the recipes every time. But yeah, because that just multiplies it by a factor of like how many stones there are, the number of edges that you have. Okay. So we'll move on to the next question. I think this one is a little bit less wordy, at least, than Golden Stone. Definitely, Golden Stone has a lot of taking a lot of input and stuff. Let me get a link to this. So there's a link to this problem, and this is a string problem. So a hint, straight up hint, is that last time, right, we did Dijkstra's and Bellman-Ford. So this is kind of like, culmination of all the algorithms that we have. What is the last algorithm we haven't talked about? So I'll give you guys a little bit of time to read the problem. All right, great. So general gist of the problem, right, is you have two strings. They're going to give you two strings, and they're going to give you a bunch of kind of character transformations that you can do one by one on each of the strings. And what you want to do is you want to figure out what is the minimum cost to make both of the strings the same. So want to keep in mind that you can make modifications to both strings, and you do it one character at a time. So you take one character and you switch it to another one based off of what kind of allowable transformations you can make. Yeah. So following the hints, it doesn't really matter what order that Valera changes the letters in, as long as the final result, right, is equal strings. So if if Valera does the first character, first letter first, or does the last letter first, doesn't really matter. And then I want to think about how we can find the cheapest way to convert two letters into a common one. So, or if it even is possible, because sometimes it might not be possible. And then we'll kind of talk about what graph we're going to use. So first off, we're going to do some of the edge cases. So if the strings aren't guaranteed to be the same length. So obviously, if they're a different length, it's impossible to add a character onto the end. So we're going to skip that edge case. And then if you look at the problem, it kind of gives you a nice hint at what you want to use. But actually, the 500, there's actually less vertices that we're going to end up using in our graph. So we're going to use the graph that we're going to consider is going to have vertices on characters or on letters, and the edges are going to be kind of like the transformations from one character to the other. So it's going to, and they're going to have weights of the kind of like the cost associated with each one. So then we're going to use Floyd-Warshall to find the cost to convert one character to another using that graph. And since that graph only has 26 possible edges or 26 possible vertices, that's definitely going to fit within time, right? 26 cubed is very, very fast, almost constant time. Maybe not, almost constant time. And the number of edges are also pretty low, only 500. So definitely something that you want to pre-compute though, because if you do that for each one of the characters in the string, it's going to be a lot slower. But since it's the same across all the characters, we can kind of do it at once and do it right in the very beginning. So then we iterate over the string, and for every pair of letters that we choose, we want to see what is the minimum cost to reach it, to have them be equal characters. So since it's only 10 to the 5, we can actually consider all 26 possible characters to make them kind of converge at. And so we just check all of them for every single one. So it's just 26 times 10 to the 5 operations, basically. So the complexity definitely fits within the time limit. The Floyd-Warshall is barely even noticeable, and the bulk of the computing time will be going through each one of the characters in there. And yeah, does anyone have any questions about that? All right. Thank you guys so much for attending the Advanced Track first workshop. We appreciate you guys all coming. We got to see some interesting problems. Golden Stone is definitely my favorite shortest path problem because it doesn't look like a shortest path problem at first, or at least I didn't see it as it. So I hope you guys can actually attempt it because it's kind of satisfying. It's also kind of long, lots of cases that you need to consider. If you have any comments, questions, or concerns about the track and how it was run, the workshop, please fill out the feedback form. It is in the slides, link in the slides, and you can find a link to it here. And here's some problems related to what we talked about today. Feel free to work on them in any order. I think it's generally ordered in difficulty, but you might want to look through all of them. I think some of them are fairly hard. So if you get stuck, don't need to worry about it too much. So we have 30 minutes left. So we're going to spend the rest of the time working on problems, and discussing any. If you're confused about anything or you want help with the Dijkstra's implementation, just reach out. All right. Thank you.